Imagine holding a cup of fluid and the fluid just spontaneously overflows from the rim even though you didn't even tilt the cup. Doesn't it seem impossible for that to happen? Well, there are fluids that actually behave in such a way, and these fluids are known as superfluids. Superfluids are fluids that exhibit bizarre behaviors and are able to do things that no other fluids can. Superfluidity is a state of matter in which all atoms of the superfluid are in the same quantum state, which results in its unique behavior and will be further explained later on. In normal liquids such as water, the atoms move in a random motion where particles in the liquid vibrate, move, and slide past each other freely. This is unlike the atoms in a superfluid, where the atoms lose all their randomness and move in a coordinated manner instead, so that the fluid does not have friction with itself. Helium-4 at extremely low temperatures of below -271 degrees Celsius, which is also known as a lambda point, will become superfluids and will be the main type of superfluid mentioned in this video. Even at temperatures nearing absolute zero, which is 0 Kelvin, the zero-point motion of helium atoms is still large enough to prevent them from solidifying. Zero-point motion refers to the slight jiggling of atoms in the lowest possible energy state. As such, helium atoms will only solidify under high pressure, as they are so light and have very weak intermolecular forces of attraction, which allows them to become a superfluid instead of a solid at very low temperatures. Helium-4 is a non-radioactive isotope of helium and makes up 99.9% of the helium on Earth. Helium-4 as a superfluid is a fluid with zero viscosity, which means that it flows without friction with itself. The more viscous a fluid is, the more resistant to flow it is. Helium-4 has a nucleus with 2 protons and 2 neutrons, and the nucleus is surrounded by an electron shell with 2 electrons. Since the number of particles that the atom comprises of is an even number, Helium-4 is a boson, which are elementary particles with the property that any number of them can occupy the same quantum state. This is the unique property of superfluids that allows it to flow without any resistance with itself. As a result, they will all have the same momentum, so that when one of the atoms moves, all the other atoms will move together with it, behaving like a single atom, somewhat like a group of people in a marching band. The wave function of bosons tend to overlap, and when they overlap, they begin to align themselves with each other, forming a synchronized wave function. The individual particles will lose their individual identity and form a Bose-Einstein condensate, a state of matter of a dilute gas of bosons, cooked to temperatures very close to absolute zero. Under these conditions, most of the bosons occupy the lowest quantum state, which means that it is in the ground state and has very low energy, known as the zero-point energy. As a result, superfluids will not be able to convert into any other kind of energy, which means that it has zero entropy. This is due to the fact that it theoretically possesses the lowest possible energy that it can have, and thus does not have enough potential energy that would allow it to convert into other forms of energy. Another property that results from superfluids behaving like one single atom is that it has infinite thermal conductivity. This means that for superfluids of any volume, it will always have the same temperature throughout the fluid. This is because superfluids transfer heat almost instantaneously, creating thermal waves, which is a sound wave in a solid with a very short wavelength. This phenomenon occurs because superfluids behave like one atom, thus virtually no time is needed for transfer of heat throughout the superfluid. Superfluids can even creep up and over the sides of a container, seemingly defying gravity. This is due to a special type of surface wave found in superfluids that pushes this very thin film up the sides of a container, known as third sound. For other fluids, when the film of fluid is particularly thin, the friction against the surface will be so great that it stops the fluid from moving at all. On the other hand, superfluids will still be able to form waves which is alternately higher and lower than the fluid surface, as it has no internal friction. This special type of surface wave, in which only the superfluid is moving, is known as the third sound, and is what causes the superfluid to be pushed up the container. Superfluids sure seem to be an absolutely mind-blowing fluid. Who knows though, maybe one day we'll find yet another kind of fluid that exhibit properties even stranger than superfluids.